Welcome to the Explainer. Today, we are taking on a concept from the Cambridge Mathematics syllabus that literally trips up thousands of students every single year. We're talking about Surds. Now, I want you to think completely differently about how you approach your math exams. Doing Cambridge Mathematics, especially at the highest level, isn't just about frantically crunching numbers on a calculator. Honestly, it's a lot more like being a master sculptor. You start with this raw, heavy, unrefined block of information, and your goal is to deliberately chip away all the irrelevant material to reveal a perfect, exact, incredibly elegant masterpiece underneath. In the exam room, we see two types of students. You've got students, let's call them the Alexes, who just overload their answers with raw, messy mathematical facts from their calculator with absolutely no analysis or refinement. And then you have the Sams, who rush through, completely missing the command word requirements to leave things in an exact form. We are going to make sure you don't fall into either of those traps today. So grab your chisels, get focused, and let's get to work.
Right off the bat, take a look at this number on your screen, 1.414213,562. It's highly specific, it's exceptionally long, and let's be completely honest with ourselves, it is incredibly messy. This trailing endless decimal is exactly how most untrained students view mathematics. They see a problem, they panic, they punch a calculation into their device, write down this long chaotic string of numbers on the answer line, and they think they've actually found the ultimate truth of the problem. They think they've secured the marks. But here's the reality check. In the eyes of a Cambridge examiner, a decimal like this is often nothing more than a rough sketch. It's a placeholder. It's not the masterpiece. It's the debris left on the floor of the studio.
And this contrast you're seeing right now brilliantly illustrates the absolute core of our explainer today. On the left side, we have that flawed, chaotic, never-ending decimal approximation. But look at the right side. On the right, we have its true, exact, entirely uncorrupted form, the square root of 2. Leaving your answer in this exact form, which we call a surd, is vastly superior in Cambridge exams unless the command word of the question explicitly, specifically asks you to round to a certain number of decimal places. You really need to internalize this. The decimal is just an approximation. It's close, but it's not perfect. The surd, however, the surd is absolute mathematical perfection. It is exactly the value it represents, nothing lost, nothing rounded. So, to turn you into that mathematical sculpture we talked about, here is our roadmap for today. First, we'll dive into the nature of surds. Then, we'll outline the essential rules of manipulation. From there, we move into the actual carving with sculpting and simplifying, followed by expanding expressions. Finally, we'll finish off with the masterstroke, rationalizing the denominator. Let's jump in.
Number 1, the nature of surds. Before we start swinging our chisels around, we really need to understand the unrefined blocks of marble we are actually going to be working with.
So what exactly is a surd? Well, by definition, if a root cannot be written as a rational number, like a clean, simple fraction or a whole integer, it is known as a surd, or sometimes called a radical. Because they absolutely cannot be expressed as simple fractions, surds are inherently irrational numbers. Think of the square root of 2, the square root of 3, or even something like the fourth root of 10. They represent a perfectly exact, unbroken value. Now, to put that into perspective, the square root of 16 is just 4. That's a nice, clean, rational answer. But the square root of 2? That doesn't break down cleanly. It remains a surd. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Now, it is totally fascinating to see how our everyday tools handle these pure values. On the left, we have a Texas Instruments calculator trying its absolute best to resolve a surd expression. And what does it do? It spits out a messy decimal, 4.732050808. It essentially just gave up and approximated the answer. But look over on the right. The Casio calculator is engineered to maintain that mathematical purity, returning the exact surd output of 3 plus the square root of 3. That exact output on the right is your ultimate goal. That is what guarantees you those top-tier marks when the examiner is looking at your working out. Moving on to Section 2, Essential Rules of Manipulation. Now that we know what our raw marble looks like, let's carefully look at the tools we need to manipulate these numbers, without accidentally shattering them. Think of these rules as your mathematical chisels. They are what allow us to combine and multiply surds cleanly and safely. The absolute golden rule here is that the square root of a multiplied by the square root of b equals the square root of a times b all together under one roof. So for example, the square root of 3 times the square root of 5 combines beautifully into the square root of 15. You just multiply the numbers inside. And guess what? The exact same logic works for division. The square root of a divided by the square root of b
simply equals the big square root of the fraction a over b. These rules are absolute bedrock. They will never, ever let you down if you apply them correctly.
But listen to me carefully, you have to be on high alert, which brings us to the danger zone. This is exactly where so many students crack their marble and lose easy marks. The square root of 4 plus the square root of 9 absolutely positively does not equal the square root of 13. I see this mistake all the time. Why is it wrong? Well, let's just do the math. The square root of 4 is exactly 2, right? And the square root of 9 is exactly 3. 2 plus 3 equals 5. But if you punch the square root of 13 into a calculator, it is far, far from 5. So the absolutely crucial takeaway here is this. You can only add or subtract surds if they are multiples of the exact same identical root. You cannot just mash them together.
Number 3, sculpting and simplifying surds. Let's move to the really satisfying part of the process. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to free grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, getting back to it. This is the active process of taking large, bulky numbers trapped under a square root and breaking them down into highly elegant, simplified forms. If a surd cannot be simplified any further, like the square root of 17, for instance, then it's already in its most basic form. You leave it alone. But many non-prime numbers actually hide perfect squares deep inside them, just waiting to be carved out. To simplify these, we systematically follow 3 steps. First, we hunt for a hidden perfect square factor within the block. We are actively looking for numbers like 4, 9, 16, 25, or 121. Second, once we find it, we write the original number as a product of that perfect square and whatever is left over. Third, we simply take the square root of that perfect square and we pull it completely outside the surd.
Let's see how this logic builds in a real exam-style example. Take this incredibly bulky square root of 363. Step 1, we hunt for our perfect square. You might try dividing by 4, then by 9, but eventually you'll find that 121 goes into 363 exactly 3 times. Step 2, we rewrite the expression under the root as 121 times 3. Now for the magic. Step 3, we know that the square root of 121 is exactly 11, so we chisel that part out. We pull that 11 completely outside the root symbol, leaving the 3 safely inside. That leaves us with a wonderfully elegant, totally simplified final answer of 11 root 3. Look at that. We've successfully chipped away all the excess mathematical material. Moving right along to Section 4, expanding surd expressions. Because, let's be real, exam questions are rarely going to just hand you a single isolated number to simplify. We need to look at scenarios where surds are grouped together inside brackets. All right, here we have a classic textbook Cambridge-style bracket expansion. Bracket 2 plus root 3 multiplied by bracket 3 minus root 3. Now, don't let the surds intimidate you. Just like basic algebra, we are going to multiply both terms in the first bracket by both terms in the second bracket. We start with 2 times 3, which gives us 6. Then 2 times minus root 3, giving us minus 2 root 3. Then the inside terms, positive root 3 times 3 gives us positive 3 root 3. And finally, positive root 3 times negative root 3. Well, a root times itself just cancels the root out, so that leaves us with a clean minus 3. Now notice how those messy middle terms interact? We have a minus 2 root 3 and a positive 3 root 3. It's like a tug of war, and we are left with just a single positive root 3. And looking at our whole numbers, 6 minus 3 is just 3. So that whole big, complex double bracket expression simplifies incredibly neatly down to just 3 plus root 3. Absolutely beautiful. And finally, we arrive at Section 5, rationalizing the denominator. This is the master level stage of our sculpting metaphor. This is all about polishing the base of our mathematical expression so the whole thing stands perfectly on a rational, solid foundation. In high-level mathematics, leaving a surd in the denominator, meaning the bottom part of a fraction, is considered highly unpolished. It's like trying to display your beautiful marble statue on a base that isn't flat. To fix it, we have to eliminate the surd from the bottom without actually changing the fundamental value of the fraction itself. So how do we do that? By multiplying the fraction by a cleverly disguised number 1. For the fraction 1 over root 2, we multiply it by root 2 over root 2. Why? Because root 2 divided by root 2 is just 1. But watch what happens. Root 2 times root 2 on the bottom gives us a perfectly clean rational 2. The top just becomes 1 times root 2, which is root 2. We are left with root 2 over 2. The value is exactly the same, but the base is completely rationalized. But what if the exam paper throws a much more complex base at you? Take a very close look at this one. 1 over 3 plus root 2. Now, if you try to use our previous trick and just multiply the top and the bottom by root 2, I promise you it is not going to work. Think about it. On the bottom, you would have to distribute that root 2. You'd get 3 times root 2 plus root 2 times root 2, which is 2. So the bottom becomes 3 root 2 plus 2. You haven't actually eliminated the third at all, you've just annoyingly moved it over next to the 3. So we clearly need a much stronger tool for this specific job. And here is that ultimate polishing tool I promised you, an elegant algebraic principle known as the difference of two squares. You've probably seen this before. It states that bracket a minus b multiplied by bracket a plus b equals a squared minus b squared. Now, this formula is pure, absolute magic when it comes to surds. Why? Because notice that there is no middle term in the result. It's just a squared minus b squared. So if a or b happens to be a surd, squaring them will completely and utterly destroy the square root, absolutely guaranteeing that the resulting answer will be a perfectly rational whole number.
Let's actually apply this algebraic magic to our complex space from earlier. We have 1 over 3 plus root 2. We need to multiply the top and the bottom by its exact counterparts, just with the sign flipped. So we multiply by 3 minus root 2 over 3 minus root 2. Let's look at the bottom first. This is where the difference of two squares kicks in beautifully. It simply becomes the first term squared minus the second term squared. So that's 3 squared, which is 9, minus root 2 squared, which is just 2. So we have 9 minus 2, which equals exactly 7. No more surds. On the top, we just have 1 multiplied by 3 minus root 2, which stays 3 minus root 2. So our final, perfectly polished, incredibly impressive answer is 3 minus root 2 all over 7. The surd is completely eliminated from the denominator, and the examiner is going to give you full marks.
So, as we wrap up this explainer, I want to leave you with a really provocative thought about mathematical purity. If decimals are just mere approximations, just rough sketches of the truth, are you really truly solving the mathematical problem if you abandon the exact surd halfway through? To excel in Cambridge mathematics, you need to stop frantically rushing to the calculator the second you see a square root. Treat every single equation like a raw block of marble. Use your rules carefully, simplify methodically, expand systematically, and always rationalize your denominators. Embrace the exact form, and you will reveal the masterpiece hidden inside the math. Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, AC Exams, at @ACExams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @ACExams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. AC Exams, your Cambridge success starts here.